Hello there, ladies and gentlemen. I am going to make a video that covers the answers to Worksheet 3 and plenty of explanations. So let us start at the beginning. Let's open our notebooks and find Worksheet 3. It's on page 60. I don't really know what page it's on. It's on 60 something. If you look at the top, it should say Matt Worksheet 3. Look how good that handwriting was. Okay. So, and of course, feel free to pause at any moment as you need to go back and watch something again. So number one says elements in the same, obviously it's grouped because it's circled, at the same number of valence electrons, though they may be in different energy levels. So I'm going to hit this idea of how can I figure out the valence electrons in a second. If you look at a periodic table, there's a lot of different periodic tables out there. But let's say that we were doing the element that is right here, boom. And that element is called germanium. Yeah, it's called germanium. I have a periodic table behind me. And so germanium, I'm going to do this long, and then we're going to do this slow. Germanium is 1s, 2, boom, 2s, 2, 2p, oops, still I'm not recording that, 2p, 6. And I got to keep going, right, until I get to whatever germanium is. And so we go for a while, and now we're finally at the exciting part. So we went through the 1s, and I'm just going to point this out. We went through, why did it go down there? I hate you. We went through the 1s, then the 2s, then the 2p, and then the 3s, and the 3p. Now my dog is barking like crazy, but we're going to ignore that. And then we're going to work our way across to here. Okay, boom, 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 boom. And, oh no. All right, let's keep going here. So what is after the 3s? 3p6 is 3s2. We keep building up these electrons. And then the d's are out of order. If you remember from off-pause order, the d's are a little bit out of order. So 3d and then 10. And then this particular element, which is germanium, is 4p2. Now, question up there was really about the valence electrons. So I want to hit on an idea here. Valence electrons are the electrons in the outer energy level. So valence, the electrons on the outside. Okay, so they're on the outside. They're the outside layer of electrons. And so when I look at this configuration for germanium, I'm going to point out that this and this, these two, are the outside because the fourth level, this amazing box mate, the fourth energy level is farther away than the third level, which is farther away than the second level. And of course, the closest to the nucleus is the first level. So these values in front are the energy levels, and they tell us how far away from the nucleus. Well, how many electrons does this element have on the outside? It has, that was the wrong button, it has 4 valence electrons. It has 4 electrons on the outside. So, if we were to do another element, and let's pick the element right before it. If I pick the element right here, let's call this, right, this one here, it would be almost the same, except the very ending would be 1, and then we would say 3 valence electrons, right? Because it's the one right before that one. I have 3. And what was realized after a while is that if you count across on the periodic table, the first column is always going to have 1 because it's going to be 1s1 or 2s1 or 3s1 or 4s1 or 5s1. And the second column is going to have 2 because it's 4s2. And then after the 2s, you might have the d's, but the d's are always a lower energy level. So it's still 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2. And then it picks up again. When you get to this column, they're going to have 3, and you're going to have 4 and 5 and 6 and 7. And I can talk a lot faster than I can write with a mouse, that's for certain. Man, my handwriting is awesome. Reminds me of one of my students. There we go. So 1, 2, 3, 4, 5, 6, 7, 8. That's how many valence electrons an atom has And the reason for that is like this element here. Let's just pick this one here that I've now scribbled in. On the outside, it's going to be 1s2, 2s2, 2p6, and then the outside would be 3s2, 3p, 5. So what is 2 plus 5? It is 7. And so the element that's here is going to have 7 because it's got 2 on the outside and then 5 more on the outside. So valence electrons are all about who's on the outside. Everyone in this group, called the halogens, would have 7. All right. Speaking of halogens, number 2, name one element for each of the following groups or families. So I grabbed this periodic table from somewhere. In fact, it says it on the bottom, but it has labeled that the first column is alkali metals, the second is alkaline earth, middle is transition, noble gases, and halogens are in the green. So if you wrote down any element inside one of those, you are good to go. Okay. Now, number 3, elements in the same blank have the same energy levels. That's period. So the energy level is those numbers in the front. And every element that's here has gone through 4 energy levels. They're going to have the first energy level. They're going to have the second energy level. They're going to have the third energy level all the way across, and the fourth energy level. Each of those elements is going to have the same number of periods and energy levels. And these are the periods 1, 2, 3, 4, 5, 6, 7, and they correspond directly to the energy levels that have been filled up so far. So if you're dealing with an element down here, it is 6 periods down, so we'll have 6 energy levels of electrons. Alrighty, how do they compare in terms of the following things? Atomic size. Cesium is larger than sodium. We talked about atomic size in the notes, and we said this: as we go down the periodic table, atomic size is increasing. And since cesium is down here and sodium's up here, so cesium is going to be bigger. Why is it bigger? It has more energy levels. As you go down, there's more and more energy levels, like we just said. There's more layers of electrons. Cesium being farther down, it's going to have more energy levels, and therefore bigger. How about the number of outer shell electrons? Well, they are both going to, what's another word for outer shell electrons? Let's type that in there. Another word for outer shell electrons is valence. They're going to both have the same number of valence electrons. They're going to have 1 because they're in the same column. Ionization energy. This is the energy it takes to remove an electron. How hard is it to remove an electron? That's what ionization energy is. And the trend was, as we get closer to helium, it gets harder and harder. You have to put more and more energy in. If you get closer to francium, it gets easier and easier. So it's very easy to steal from francium, harder to steal from helium. And then what about the common ions? We're not actually dealing with that right now. Cesium and sodium both have 1 valence electron that they often lose, which is why they take a +1 charge. But that's really going to be a later conversation. Okay, number 5. Again, which one is larger in atomic size? So if it's larger, it's going to be closer to francium and farther away from helium. So atomic size increases as you get closer to francium. And there are some wobbles to every trend, but we're not talking about the wobbles. We're talking about the basic trend. So if you compare the location of sodium to the location of silicon, which one of those elements is closer to francium? Heck, it's pretty obvious that sodium is closer to francium, and it would be bigger. And that's what's going on in number 5, just figuring out who's closer to francium and therefore a bigger atom. And then which element would have a lower ionization energy? So if an element is big, bug elements, nice. Big elements have electrons far away from the nucleus. So when they are big, like those elements in the bottom left, it's going to be a lot easier to remove those electrons than the ones that are near the top right, which it gets harder and harder to remove. So it's the same trend, but just the reverse concept. So as we get closer to francium, the energy to remove an electron decreases. As we get closer to helium, the energy to remove an electron increases. It's very hard to steal from helium. You have to use a lot of energy to do it. It's very easy to steal from francium. It doesn't require much energy. So again, you just kind of look at the position of the elements. And I want to point out that 5 and 6 are actually the exact same elements. Okay, number 7. Which element would have the greater shielding effect? Shielding effect is really about the number of energy levels being used. And so whichever one has more energy levels, it's going to have more shielding because each energy level shields or repels the other energy levels. So since cesium has more energy levels, it would be greater. Cesium has more than aluminum, so it would be greater. Aluminum and sulfur have the same number of energy levels, so they would actually have the same amount of shielding effect. And then gallium has more energy levels, so it would be greater. Number 8, another one of these, comparing aluminum is larger in size, it's closer to francium. Number of outer shell electrons, aluminum has 3 if you look at the valence. Chlorine has 7 if you look at the valence. So aluminum has a smaller amount than chlorine. I don't really like the question, just the concept. So aluminum has 3, chlorine has 7, aluminum has fewer valence electrons. Ionization energy, it would be easier to take electrons from aluminum than from chlorine. Again, we said as you get closer and closer to helium, it gets harder and harder. You have to put in more energy. So taking from chlorine would require more energy than taking from aluminum. Again, we're not worried about the ions they make. What is the noble gas configuration, and draw the orbital diagram? So noble gas configuration is the shorthand. And here's how you do a noble gas configuration. I have to scroll down so you can see an example of it. In this example, they want to find zinc. So what they do first is they find the element on the periodic table, boom. Then they find the symbol for the nearest smaller noble gas. So what is smaller than zinc? Well, it's not krypton. Krypton is beyond it. So you got to go back one level. Argon. Argon is before zinc. So you start off by writing down argon because that's the noble gas. And then to get to zinc, you start at the 4th energy level, so these are the 4 S's, and then you have all the 3 D's. So that's how you do a noble gas configuration. And that's what's going on here in number 9. What is the nickel's noble gas configuration? So you find nickel. Nickel is right here, boom, and you build up to it. So you say nickel would be all these pieces, and then it would have this extra stuff afterwards. So nickel is argon, 4s2, 3d8. Why do we group elements in families? Well, we don't. Dmitry Mendeleev actually did that. When he did it, it was because of their properties, the way they reacted. Nowadays, we know that the reason they react the same is because they actually have the same valence electrons. So fluorine, chlorine, and bromine, who are all halogens, behave similarly because they have the same on the outside. Why do we group elements in periods? Well, that's because of energy levels. That's where we're seeing the same energy level of electrons. What does the term ionization energy describe? It's how much energy you have to put in to take an electron. I mean, imagine you're trying to take something from 2 different people. It might be easier to take from one than the other. That's all ionization energy is. How much energy does it take to take the electron? Aluminum plus 3 is smaller than neutral aluminum. Why? That would have lost some electrons. Hey, look, I found a couple of cool periodic tables. This periodic table here kind of shows us where the S, P, D, and F areas are of the periodic table. This periodic table here, they took this F area and they squeezed it in there. Look at that. We got the 1s and the 2s, we have the Fs, the Ds, and the Ps. That's a pretty cool periodic table. I like that one. Write the noble gas configuration for the following elements. Oh, write electron configurations. So let's just try that. Oh, cobalt. I'm going to go back and find cobalt on this periodic table. Boom, bitty, boom, bitty, boom. I'm going to go find it ooh, that's way too small. Fool. There we go. Okay, let's find cobalt on this wild periodic table. Cobalt is right here. So in order to get there, we have to go from the 1s to the 2s to the 2p to the 3s to 3p to the 4s, And then 3D, 1, 2, 3, 4, 5, 6, 7. It's the seventh one over. So that's what we have here. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d7. On the back of your periodic table, you have off-Bowles order. Totally fine if you use off-Bowles order to do that. I am just enjoying pointing out that the periodic table is actually in off-Bowles order. I repeat that. The periodic table is actually in off-Bowles order. Okay, number B, there's the configuration. And then the orbital diagram is the arrows that represent those electrons. When you're doing these diagrams, don't forget, if you're doing an S, let me grab some tools here. The S should be 1 box. The P's should actually be 3 boxes. And I know I'm not making them proportional in size. Just deal with that. S is 1 box. P's are 3. And then as you go to put the arrows in, if it's full, you should have 1 up and 1 down. If it's not full, you're supposed to spread them out. So what happened here is they did up, up, up. And for the 4th arrow, they put it down. So you do all the ups and then come back and do the downs. It's also how I approach my homework. I do the things that are bring me up, up, up before I do the things that are going to bring me down. No, that's not true, but maybe that resonated with some of you. More diagrams. And look, here's another periodic table. In fact, I've hidden the answer, but if I look at just the end, 4p6, I should be able to figure out what element that is. 1, 2, 3, 4 levels down, and it's the 6th one over. 1, 2, 1, 2, 3, 4, 5. So that should be krypton, right? Oh, look at that. It is krypton. Remember, if it's in the first column, it's S1. So if I talk about strontium, that's 5 levels down, 2nd column. So that would be 5s2 at the very end. Another periodic table. All right, what was that at the end? Just a second. This is not that. I don't know why that's there. This, I think, is magnesium. Yeah, that's magnesium. I'm not sure why it says vanadium right there. Okay, we scratched out 15. We're not really dealing with wavelength and all that stuff. What is shielding effect? That's one thing we hit briefly earlier. Shielding is when you have all of these layers of electrons, and the layers of electrons are repelling each other. Look at this great diagram. So this is a Bohr model. We have the nucleus with 11 protons and 12 neutrons, and then we have a layer of electrons, and then we have another layer of electrons, and then we have the outside. You remember the outside is called the valence. And so the 10 electrons that are on the inside, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Those 10 electrons on the inside are going to push the electrons that are on the outside. And so we're saying that those 10 on the inside, which are pushing, are shielding the nucleus from the outside. And the more layers of electrons, the more shielding. This is the same concept, but it's a different element. So look, this one had 2 layers. This has 2 layers. The outside is different, but the inside is the same. So both sodium and chlorine have 2 energy levels before the valence. They have 2 layers of shielding. And then this is that trend we were talking about earlier about atomic radius and ionization energy. He is the smallest. Helium, is the smallest. And then francium is the biggest. He is high energy. Francium is low energy as far as ionization energy. All right, that covers everything on Worksheet 2. I hope you've enjoyed this Worksheet 2 review and that you're ready to move on into the future where electron configurations can give